Qualichem, supporting the water treatment community since 1990. Qualichem offers some of the best formulation expertise in the industry. Qualichem offers a wide array of house formulations, or Qualichem can help you with your own formulations. At Qualichem, we never sell direct to the end user, so you'll never have to worry about competing with your blender. To find out more about Qualichem, go to scalinguph2o.com/Qualichem. Once again, that's scalinguph2o.com/Qualichem. At Qualichem, we know the blender matters. You're listening to the smooth sounds of water treatment knowledge with Scaling Up H2O. Your host, Trace Blackmore. What the heck did you just tune into? Sorry, folks, having a little fun with our intro. Of course, this is the Scaling Up H2O podcast, and it's still the podcast where we're scaling up on knowledge so we don't scale up our systems. And I am still Trace Blackmore, certified water technologist, and your host for this awesome podcast. And of course, it's always awesome because of our listeners. I'm here in the studio, and I just wanted to have a little fun with the intro. I'm sure that's probably not your favorite intro, but I thought I would have a little fun with it. So thank you for going on me with that journey. And today is going to be a journey because this is a Pinks and Blues episode where we are opening up the Scaling Up mailbag to answer your questions. That's right, the questions from the Scaling Up Nation. And we've picked one specific question out that we are going to talk about today, but I'm going to leave you in suspense just a little bit. There are a few items that I want to make sure you know are available for your educational enjoyment, and that is a few organizations are having some events that you might want to know about. First up is the Water Environment Federation and International Water Association. They are holding their Innovations in Process Engineering Conference June 6th through June 9th in Portland, Oregon. So this is where process engineers come together for a cutting-edge showcase on everything that is innovative around new practices in water resource recovery. And this conference will focus on a large range of topics, including to resource recovery, treatment efficacy, efficiency, and enhancements. To learn more about this, we're going to have all of that information for you on our show notes page. The Water Environment Federation is also holding their Collection Systems Conference June 27th through 30th in Kansas City, Missouri. We will have all of that information for you on our events page. And then finally, the National Rural Water Association is having their Water Pro Conference September 25th through 27th in Aurora, Colorado. More information is available on this right on our show notes page. And Nation, speaking of our show notes page, I know we mention a lot of conferences on this show, but we make it so easy for you to find everything we talk about, not just the events, but everything we talk about is searchable on scalinguph2o.com. So many people are learning that search feature is their gateway to so much knowledge about whatever they want to learn more about. So I urge you, if you have not been to scalinguph2o.com, please navigate over to that page, and I know you will be glad that you did. Something else that you will be glad that you did is listen to this latest installment of Periodic Water Table with James.
Hello and welcome to the Periodic Water Table with James, where we think and learn about water chemistry drop by drop. Please use your week to search online, ask your colleagues, or even pick up a book to learn more about each week's periodic water table topic. If you do, at the end of the year, you'll be 52 water chemistry smarter. So let's raise the water table of knowledge together and get started. Today's topic is HEDP. You might already know that HEDP is a phosphonate, but what does that mean? What does HEDP stand for? What is its molecular formula? What percentage of HEDP is phosphate? Is HEDP used for scale control, corrosion control, or both? Is HEDP synergistic with anything else? Does pH have an impact? Can HEDP precipitate with anything? If so, how might this be controlled? Do oxidizing biocides, such as chlorine, have an impact upon HEDP? How does this impact compare to that of other phosphonates? Do you use any products with HEDP? Remember, knowledge is power, and taking the time to learn more about water chemistry each week will help make you a force to be reckoned with. Be sure to post what you learned to social media and tag it with hashtag WaterTable23 and hashtag ScalingUpH2O. I look forward to learning more from you.
As always, thank you, James, for bringing that to us each and every week. And Nation, there's not a week that doesn't go by, hardly, where I am not asking for what your ideas are, for what your questions are. And today, I am going to answer those questions. We call that a Pinks and Blues episode, and today we are taking multiple questions about what is the difference between conductivity and total dissolved solids. Lots of people have asked questions about this. Lots of people are asking questions that they have meters that have both buttons to read conductivity and TDS. And what exactly is the difference there? And that's what we're going to talk about. First off, I want to talk about conductivity. So let's start out with talking about what conductivity is. And think about that word. I love using words to define itself, to define that word. So conduction. How are we conducting a current through water? So you've either done this experiment that I'm getting ready to talk about, or you've seen an illustration of it. So if we have ultra pure water, so let's say we've distilled water, so it has nothing dissolved in it, we put that in water and we put a current across that pure water and we stick a light in that water, it will not illuminate. It will not illuminate because there is not enough solids dissolved in that water to conduct the current across the water so we can complete the circuit. Now, you've also seen that same experiment where they've dissolved solids in that water, and it's those solids which are creating little bridges for that current to go across the water and connect the circuit. This is conductivity. We're able to conduct the current across the water. So now think of your conductivity meter that has that button that you hit that says conductivity on it. What exactly is going on there? So you put your water sample in that little cup, and in that little cup, you're going to see two metal pieces, probably one on the bottom and one that sticks out from the side. Well, whether you knew it or not, what that is an anode and a cathode. One is positively charged, one is negatively charged, and we're going to put a current across the water, and we are measuring how easily that current goes from point A to point B. And whatever that is now translated into conductivity. We're actually able to conduct that electrical current from point A to point B. The more solids that you have in the system equals the easier it is going to be to get that current from point A to point B. That's what conductivity is. And then through years of measuring conductivity, we've been able to equate that in industrial water treatment. So we know that we can set our controllers up to measure so much conductivity before it opens up a bleed solenoid. And we know that the solution to pollution is dilution. And what's going on there is that high solids water, that high conductivity water that's in, say, a cooling tower, is now being bled out and it's being replenished by low solids, low conductivity water. So the solution to pollution is dilution. Well, I guess we can also say the solution to concentration is dilution, but that doesn't rhyme, so we're not going to say it that way. So that's what conductivity is. Now, conductivity alone doesn't tell us a lot. Conductivity tells us the sum of the parts, if you will. Conductivity tells us that all of the things that are dissolved in the water equal the conductivity. So what's dissolved in the water? Well, that's why you are running your tests. So you might run a chlorides test, you might run a hardness test, you might run an iron test, a copper test, a phosphate test. Whatever it is, all of those things are dissolved in the water and they are contributing to conductivity. Now, what we have done is we've taken our products and we know our products are able to hold so much of stuff, those things that we're measuring, into solution until there's an issue. So we know that as long as we stay under certain concentrations of, say, calcium or certain concentrations of silica, and you name it, that's what our technical directors are doing. They're figuring out how much we can hold of a particular substance in solution, and then that allows us to equate that to conductivity. And we say that we don't want our overall system conductivity to exceed, and I'm just going to throw out a number there, say it's 1,000. So whenever we get to 1,000, and maybe your number is 3,000, it really doesn't matter. It's whatever the number is, that tells us to do something. Specifically, that's the controller being told to do something, and that's where the solution to pollution is dilution comes in. All right, well, that's all sounds well and good, but the question is, what's the difference between conductivity and total dissolved solids? So we know what happens when you press the button that, boom, conductivity button pressed, and we know that a charge is sent from point A to point B, and we know that the water, depending on how much stuff is dissolved in it, the easier it's going to be to get from A to B. So how do we involve TDS into all of this? Well, that's what we're going to talk about next. So let's start by defining TDS. Well, that stands for total dissolved solids. And what is that? Well, that's the total amount of dissolved solids in your solution. I love it when terms define themselves. Well, that doesn't really help us with our question here today. So total dissolved solids has also a TDS button on our meter. So we hit that button, and what's happening with that? Let's talk about if we were in the lab. So if we're in the lab not using our meter, there's a very well-defined procedure on getting total dissolved solids. So we're going to have a predetermined volume of sample that we're going to bring back to our lab. We're going to ensure that that sample is as well mixed as possible. And after we well mix this, we're going to weigh a filter paper. And then we're going to draw that sample through that pre-weighed filter paper, and we are going to dry it. Specifically, the procedure is we put it in an oven at 105 degrees Celsius for 1 hour. And then we're going to place that in a desiccator for 1 hour to cool, and then we are going to re-weigh that filter. So we have how much the filter weighed in the beginning, and then we have how much the filter weighed when we passed our sample through it, and we allowed all the water to evaporate out. So now all we have left are the dissolved solids in that filter paper. Well, we're going to take that and put it into this equation. So the filter, the final weight minus the original weight in grams times 1 million divided by the sample volume we put through it will actually equal the TDS value, how many total dissolved solids were in that filter paper. So that's the procedure. Maybe you knew that, maybe you didn't know that, but I do know you know when you hit that button on your meter that says TDS, that is not happening. I assure you, little elves do not live inside your meter and they are doing this procedure. So what exactly is going on inside your meter? Well, it's just a percentage of conductivity. So it's putting that same electrical charge through the water sample and then it's taking a percentage of that. Now, typically 65% of whatever your conductivity is what your meter is going to take a percentage of. So different meters might be a little bit different, but I think you can feel safe with 65% of conductivity is what your meter thinks total dissolved solids are. We know that there is no way your meter can actually do that because we now know the procedure involved with total dissolved solids. So why is there a button on our meter for TDS? Well, it might make you feel good to do that. And I bet if you were to do the math consistently, if you were to go into the lab, run the procedure as we just said, and compared that to conductivity, most likely you're roughly going to get all of your data within that 65 to 75% range. And that's why your meter does that. So in order to answer the questions around total dissolved solids and conductivity that our listeners have written in for us to answer on this episode, we know what that procedure actually is. We now know what our meter is doing, and we can take that information for however we want to use it. Now let's talk about that, because why do we even want to know about conductivity or total dissolved solids? Now we already talked about setting up our controller and the solution to pollution is dilution, but how do we also know how to use that? And that's where I want to talk about calcium carbonate. For those of you that have heard me speak on calcium carbonate before, I call it the water treater's nemesis, and it's because we are heat transfer efficiency managers, and I say that on this podcast all the time, and because we are dealing with heat, the thing that impedes heat the most that we deal with is calcium carbonate, and that's where 5 things come together in order to create calcium carbonate. Well, that's calcium hardness, alkalinity, temperature, total dissolved solids, and pH. Those are the 5 things. Those are the 5 ingredients a chef needs in order for calcium carbonate to be on the menu. And trust me, on the Water Treaters Restaurant, we do not want calcium carbonate on the menu. So I want to talk about calcium carbonate just a little bit so you understand it, and then we're going to relate that back to total dissolved solids and conductivity and which one that you need to use for that equation. So here is the example, or here is the equation that we have for calcium carbonate. It's 12.3 minus the quantity of the log of the calcium hardness plus the log of the M alkalinity plus the quantity of 0.025 times the temperature in Celsius minus the quantity of 0.011 times the square root of the total dissolved solids. Okay, what that gives us is the saturation pH. Now that's a term that tells us at what pH are we neither dissolving or precipitating calcium carbonate, and that's the number that we just derived through that crazy equation. Yes, there's calculators and all sorts of things that you can use, so you don't have to plug that into a scientific calculator. But if you did, you would get the same number. And I also know that by knowing that information, whatever number you're getting on whatever tool that you are using, you now understand it better, making that a better tool. Well, have you ever seen one of the slide rules that used to be used in the water treatment industry as a tool to find calcium carbonate? And the slide rule is it has a bunch of different numbers on it, and it has a window for each one of the 5 ingredients. And you adjust the slide to make sure everything lines up, and then you read the card and it tells you what your saturation pH is, and then ultimately it will tell you what your LSI, RSI, and PSI are, which I will cover in a second. But what I want you to notice, if you can envision one of those slide rules, is that conductivity is the smallest window. I mean, it is tiny compared to everything else that takes up the entire card. So all that being said, if you were trying to calculate calcium carbonate, the best way to do that is by total dissolved solids, because it's the solids that we're worried about coming out of solution. You now know what the procedure is. You know you're not doing that in the field. So you can hit that TDS button and use that number to figure out saturation pH. And really, you can hit the conductivity button and figure out saturation pH, because it's not really going to matter. What does matter is you understand what's going on with that. And now you know exactly what the difference is between conductivity and total dissolved solids. Now, I promised I was going to go through what LSI, RSI, and PSI are, since we're talking about calcium carbonate. I call that the water treater's nemesis, because it wants to come out of solution the hotter it gets. And we are heat transfer efficiency managers, and we want to make sure that those surfaces are as clean as possible. And calcium carbonate wants to scale there, making them not clean. So with all of that knowledge, LSI, the Langelier Stability Index. So this is now taking the saturation pH that we already talked about, and now we're adding another number to it. In this case, it's pH, and in fact, we're subtracting it from that. So here's how it goes. LSI is equal to the system pH minus the saturation pH. And the scale is between -3 and 3, and that anything that is less than 0 has a non-scaling tendency, and anything that's above 0 has a scaling tendency. Notice how I said that. I did not say that anything below 0 has a corrosive tendency and everything above 0 has a scaling tendency. That is not what these indices indicate. What they indicate is whether the water is scaling or non-scaling, because they are a measure of calcium carbonate. So with this, we know all waters are corrosive. Water is called the universal solvent for this reason. Now, granted, the more stuff that the water's dissolved, the less ability it has to be aggressive to dissolve that. But trust me, over time, it will. So all waters are corrosive, and now you know what LSI is. So now let's talk about RSI. RSI is the Risner Stability Index, and that equation is the quantity of 2 times the saturation pH minus the system pH. Now, this scale is between 0 and 12, and anything below 6 has a scaling tendency, where everything above 6 has a non-scaling tendency. Maybe you use RSI, and now you know where that comes from. Now, the last one is the Picorius scaling index, and sometimes I hear that as the practical scaling index. And that equation, there's actually two equations to it. So the first one, it's 2 times the saturation pH, so just like RSI, but then we subtract the pH of equilibrium. Well, what is the pH of equilibrium? Well, that's another equation, and that equation is 1.465 times the log of the M alkalinity, and then we take that quantity and we add 4.54 to it. Now, what that does, that gives us a scale just like RSI of 0 to 12, and just like RSI, we have a scaling tendency below 6, we have a non-scaling tendency above 6. So what's the difference between the PSI and the RSI? Well, the PSI, Paul Picorius, who I so badly wanted to get on this podcast, unfortunately, I was not able to do that before he passed. He came up with this formula, and what he did, he took his years of experience in water treatment to say, hey, we're not just treating any water here. We are treating treated water, and we are treating this water to extend the ability for water to hold calcium carbonate into solution, and he wanted to add that to the equation. So he came up with the pH of equilibrium. Now, I don't know where the 1.465 came from. I wasn't able to ask him, but I did ask Brent Chettle at an AWT conference, who used to be president of AWT. He was actually the original author of the Certified Water Technologist examination. I asked him the same question, and he said, I don't know where the 1.465 comes from, but I'm going to tell you where the plus 4.54 comes from. And that was the numbers didn't line up. Paul got all of his information, and he said, you know what? It doesn't line up to the RSI scale. And he looked at all of his numbers and found out that he needed to add 4.54, and then he had a very similar scale to the RSI, and that was one that people were already familiar with. So now you know a little bit more about LSI, RSI, and PSI, and you might be wondering which one is better for us to use. And honestly, it's been my experience in years of water treatment, it doesn't really matter. You know, on the surface, it sounds like the PSI should be the ones that we use, but I have to tell you, it really doesn't matter as long as you're consistent. So you shouldn't run one that somebody else in your company is not running. You should decide as a company which one of these indices that you are going to use and be consistent. And that information is now telling you information about your system. So you're already testing calcium hardness. You're already testing M alkalinity. You know what the temperature is, and I'm going to talk about temperature in a second. And then you know what either the conductivity or the TDS is, and you know the pH. So with all of that together, you're now able to figure out what's happening to all the things that are dissolved in the system when it comes to calcium carbonate, the water treater's nemesis. Use whichever one you decide that you want to use, but make it universal throughout your company. Now let's talk about that temperature. And the reason that we're saying temperature is important is because where you take the temperature really does matter. Now let's think of a comfort cooling system. So in your mind's eye, I want you to go to the mechanical room that you were last in. Now maybe you're listening to this in a mechanical room and you can actually walk through it. So you've got a chiller, you've got some condenser water, and you've got a cooling tower. So of all of those different pieces of equipment, of all the different places that water sees in that equipment, where should you take your temperature? And I really want you to do this experiment. So whatever tool you're using, whatever indices you are using for that tool, I want you to do this on all these different places. I want you to figure out the temperature of the bulk water. Now, maybe you can just simply go to your controller and see that it's 90 degrees or whatever it is. Go ahead and run LSI, RSI, or PSI with a 90-degree water. Now, maybe then you've got a heat exchanger, and that's at 100 degrees. Go ahead and run it there. And then I want you to go to the user interface, and I want you to record the hottest temperature of the refrigerant. And that number is probably going to be about a minimum of 120 degrees. That is the hottest temperature that your water is going to come in contact with, where that hot refrigerant is on the other side of that heat exchange tube, and that's the first place that you are going to get scale. If you've ever wondered why the entire system is clean, but the chiller is only scaled in a certain spot, you run this experiment and you will see that's where calcium carbonate is coming out of solution. So that's the first place it comes out. And then, of course, it builds from there. And that's how we lay down calcium carbonate. So I hope all that information is allowing you to see why it's important. We do know the difference between conductivity and the difference between total dissolved solids. We realize how we get conductivity and how we get total dissolved solids. But more importantly, we know why we use that. We know why that is important. And Nation, I am here to tell you that when you just follow procedures, that is awesome for efficiency. That is awesome for consistency, but that stinks to motivate you to become better and wiser about what it is that you do. Now, you have to walk before you run, so you do need to know those procedures before you understand the why, but everything that I just told you is the why behind that. And I hope that that has unlocked this need for you to learn more why about everything that you do. And this is just one topic. This is just from one question asking about what the difference was between conductivity and total dissolved solids. Nation, what is the next why that you have to go out there and find that information for yourself? I want to tell you that has been the key to my success. That has been the key to me never being bored in this industry, because I'm always trying to learn more why. And I can't think of another industry that allows us to learn more why than this industry. And I've said before, if you are bored in this industry, you are doing it wrong. Challenge yourself each and every day. If you are going through servicing all of your accounts the exact same way, no wonder you're bored. If you're going through your service thinking about the same things you always think about, no wonder you are bored. So I'm going to challenge the way that you are thinking and just add one word. And that word is why. Now, for all you people out there that are worried, I'm saying, hey, change your procedures. I am not. I am saying understand your procedures at a level your procedures are never going to teach you. Ask why about everything and then explore it. Now, you probably have why about 100 things. Now, if you research 100 things at the same time, you are not going to be successful. But just like we did right here, we took conductivity and total dissolved solids. That was the only why we talked about. and how much information were we able to uncover. And folks, there's way more beyond that, but that's how to do it. We might want to know, why is there all this information on the chiller interface, and how do we use that? Well, maybe we then talk with somebody that knows a little bit more about how to use the chiller interface, and then we talk with somebody in our companies that know how to use that data, just like we did here, to figure out what temperature we needed to use with our calcium carbonate calculations. So with that, what is your next why? How are you going to improve what you know, and how are you going to make this job more fun each and every time you do it? It all starts with why. Nation, I can't thank you enough when you let me know what questions you want me to answer on the Scaling Up H2O podcast. My favorite episodes to do are Pinks and Blues, because we just do just that. We answer your questions, and I need your questions. Well, Trace, how do you get our questions? And I know it's probably the first time you've ever listened to this show, if that's what you're asking, because each and every show I'm always asking about that. It is going to scalinguph2o.com and going to our show ideas page. And there you have it, folks, another installment of Pinks and Blues. Join us next week, where we will have a brand new episode for you. And until then, have a great week, folks.